So we're going to start this section on graphing motion by taking a paragraph here and trying to turn it into a speed versus time graph. So what I'll have on the x-axis then is time, measured in seconds, and I will have speed on the y-axis. Measured in meters per second. So if I read the paragraph there, suppose you are traveling at 3 meters per second and you start increasing your speed. So that's giving me an initial value there. So when time is 0, 0 on the x, my speed is at 3. I'm going to put a dot there. Then suppose it takes me 5 seconds to reach my top speed of 13 meters per second. So if I hop 5 seconds later, 1, 2, 3, 4, 5, that's somewhere on this line. I should have reached a speed of 13. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's here. We'll put in a dot there. All right. So what's happening then is you start at this 3 here, and as time goes by, your speed has to go up in order to reach that point there. So lovely. I've made our first speed versus time graph. Now, there's some information that we can calculate from this particular graph. For example, if I've gone from 3 to 13 in only 5 seconds, I must be accelerating. So that information should be on this graph somewhere. I should be able to figure out what my acceleration was. So if I were to put some notation on here then, if I started at 3 and I went all the way up to 13, 13 minus 3, that's a 10 meter per second increase. 10. And it only took 5 seconds to do that. So as far as kinematics equations go, I have a final speed, I have an initial speed, and I have a time. So I could get my acceleration from that. So let's see, Vf minus Vi is AT. So Vf minus Vi, that was 13 minus 3, is acceleration times 5. 13 minus 3 is 10, and 10 over 5 would be my acceleration, which is 2. All right, so that's how I ended up doing it with kinematics equations. If I look at this graph, 10 over 5, that's how much this line rises divided by how much it runs. And if you remember anything from grade 9 and grade 10 math, a rise divided by a run is a slope. So what I've got here is that the acceleration of a motion is the slope of its speed versus time graph. So I'm going to write that up here. Acceleration is the slope of a speed versus time graph. All right. Lovely. So that's all well and good. I've got an acceleration of 2 meters per squared here. The other feature I don't have yet is the distance. So I'm going to see if I can calculate that. I had a VF and a VI and a T. And I'm trying to get distance. So let's try 2D is VF plus VI multiplied by the time. Okay, so twice the distance would be, final speed was 13, V initial was 3, time gap was 5, 2D is 16 times 5, and 2D is, that's 80, so the distance should be 80 over 2, distance is 40 meters. Okay, lovely. So I'm just going to come back over here to this particular graph. And I'm going to do a little work on it. First off, I want to look at this little section down here. In here. Do you notice that that section happens to be 3 units high and 5 units wide? So I've got a rectangle there, and if I were to count the squares in it, 3 by 5, it should be 15, right? The area of that rectangle is 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I have 15 square units in there. And if I were to try and do this with a triangle, the area for a triangle is 1/2 the base times the height. So if I were to calculate that there, this triangle is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 10 units tall, and it's 5 units wide. So the area for that one should be 1/2 base times the height. It should be 1/2 of 5 times 10. Half of 5 is 2.5. 2.5 times 10 is 25. And if you notice, 15 plus 25 happens to add up to 40 meters. So what I've got showing there is that the distance you've traveled is the area underneath of a speed versus time graph. Let me write that down. Distance is the area under a speed versus time graph. Not sure how close to my face that writing is. It's pretty close to my face. Let's try and recline a little. Okay. So this technique then is going to let us analyze questions where the acceleration is changing rapidly. So we did multi-phase questions where you had one acceleration at the beginning and then a new acceleration at the end. Well, if you have an acceleration that's constantly changing to something else, you can use these two ideas in order to try and calculate some stuff without having to break the problem into 18 different phases, because that would be very frustrating. So I'm going to clear all this off, and then we'll try an example like that. So looking at this particular example, I have something with an initial velocity of 4 that increases their speed over a certain amount of time until they reach a maximum speed of, it looks like 13 meters per second. And they carry on at that particular speed for a while, and then all of a sudden something happens and their speed drops precipitously to, it looks like 3 meters per second, and then continues to drop until they come to a rest. So I can see that they've stopped because their speed, right, it's a speed versus time graph, is 0. So only when your speed actually hits that x-axis has your speed dropped to nothing. So what's been going on in this particular problem? Well, if we were to do this as a kinematics exercise, we have phase 1, accelerating, phase 2, where they are coasting at a particular speed, phase 3, which is the rapid deceleration, right? They're slowing down really quickly, and then a slow gradual deceleration there. So this is a 4-phase problem, which is sort of troublesome. I already have the initial and the final speeds for each stage because it's in the graph. I just need to get the accelerations and the distances covered. The times too are neatly chunked off for me. So if I were to start with the accelerations, in this first section, right, if you check up there, acceleration is the slope of a speed versus time graph. So in this particular chunk, all I really need to know is how much did the speed go up and how much time did it take, because a slope is just a rise over a run. So if I were to start counting, this particular line goes up 1, 2, 3, 4, 5, 6, 7, 8, 9, goes up 9 and over 1, 2, 3. So in section 1, the acceleration would be the rise, so it goes up 9 over 3 for a total of 3 meters per second squared. If I were to try section 2, if I'm trying to use the slope of this section here, right, this flat section, I just need to know how much it goes up or down and over how much run it has. So this particular line goes up 0 and it runs 1, 2, 3, 4, 5 squares. So it would be 0 over 5, which is 0 meters per second squared. And that should make sense. If you're cruising at a particular speed, then you aren't accelerating, either in a positive or a negative way. Section 3. In order to do my acceleration, I'm going to need to know my rise over run. So this one changes 1, 2, 3, 4, 5, 6, 7, 8, 9. It drops 10 over 2. So 10 over 2. And I need to put something in there to show that it's dropping, not rising. So I'm going to make this negative 10, as in dropping 10. So if I do that, minus 10 divided by 2 is negative 5 meters per second squared. And so perhaps you remember from grade 9 and 10 that a line with a negative slope is tipped this way, so that it is dropping as x values increase. Section 4 then.
Mr. Barrett, Ms. Howell, Ms. Peter, please call 522.
This section here, it is also dropping, so I'm going to have a negative acceleration. So A is, it drops 1, 2, 3, drops 3 over 1, 2, 3 for a total of negative 1 meters per second squared. All right, so that's this done, the acceleration part. Now I have to try the distance. So distance is supposed to be the area contained under that speed versus time graph. So I'm going to look at each section and I'm just going to chop it up into rectangles and triangles in order to figure out how much distance is covered in each phase. So in this first phase, I have a triangle that peaks there and it's sitting on a rectangle there. So this rectangle is 3 wide and 4 high. So the area of that thing would be 3 times 4, which is 12. This triangle is 1, 2, 3 wide and 1, 2, 3, 4, 5, 6, 7, 8, 9 high. Now the area of a triangle is half the base times the height. So base times height for this would be 3 times 9, which is 27. Half of that 27 would be 13 and a half. So there are 13 and a half squares in this section. All right. So in that first phase then, while they're starting at 4 and accelerating up to 13 meters per second over 3 seconds, they have covered 12 plus 13.5 is 25.5 meters.
Ms. Cool, please call 522.
Now we could have done that with the kinematics equations, and it would have required a whole bunch of algebra in order to get it done. Or you could just make a speed versus time graph and count the squares. It's up to you. Actually, it's not up to you. You have to show me that you can do this. But going forward after this, you would have a choice whether you wanted to sketch the motion or do the algebra. In this next section, section 2, that's here, I just have this giant tall rectangle. And it is 1, 2, 3, 4, 5 squares wide, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 squares high. So the area of a rectangle is the base times the height. So 5 times 13 is 5 times 10 is 50. 5 times 3 is 15. So a total of 65. Should be 65 squares in there. 1365, yeah. So in section 2,
Ms. Ryerson, please call 522.
65 meters worth of space have been covered. In section 3, with this rapid deceleration, I have a rectangle down here that's 2 by 3. So 2 by 3 is 6 squares. Then I have this triangle here that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares high, 2 squares wide. Formula for the area of a triangle is half base height. So 2 times 10 would be 20. Keep half of that is only 10. So 10 and 6 would be 16 meters in this section. And in the final section, I have just this triangle that is 3 wide and 3 high. So 3 times 3 is 9. Keep half of it because it's a triangle, would be 4.5. So we have 4.5 meters here. So if you were to ask yourself what the total distance covered is during this particular motion, I would have to take the distance in this phase, the distance in that phase, the distance in this phase, and the distance in that phase, and add them all together. So 25.5 and 65 would be 90.5 plus 16 would be 106.5 plus 4.5 would be 111. So there's a total distance of 111 meters. 11D1 if you're a Tolkien fan. I have a very busy graph for this example. We have someone who starts at 2 and then has their speed increase slowly till they reach this speed. Then they cruise for a little while. Then they start to drop in speed, come to a stop. You can see that it's a stop because they have a speed of 0. And then their speed goes negative. So if you were to think about what this motion is doing, it's getting faster and faster going forwards, and then comes to a stop, and then reverses direction. So everything here, all of this stuff underneath of the axis, is reversing in direction. So they're going forwards for this chunk, and backwards for that chunk. So if we were to go and we were to actually work out all of our sections here, I have 1, 2, 3, 4, 5, 6 sections. So let's label them A, B, C, D, E, and F. In this first section, if I want to talk about the acceleration, I have to remind myself up there that the acceleration is the slope of a speed and time graph. So in this particular section, I have a line that goes up 1, 2, 3, and over 1, 2, 3, 4, 5, 6. So the acceleration would be rise of 3 over run of 6 which gives me 0.5 meters per second squared. This section here, it doesn't rise or fall, so the slope for that one is going to be 0. That's a 0 acceleration section. In this section here, I go from this point to that point. I drop 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 over 2. So the acceleration would be negative 10 over 2, which is negative 5 meters per second squared. This section here, I'm neither rising nor falling, so this is another section where the acceleration is 0. And in this section, I go up 1, 2, 3, 4 over 2. So the acceleration before over 2 is 2 meters per second squared. And in this last section, I go up 1 and over 3. So my acceleration would be up 1 over 3, which is approximately 0.333 meters per second squared. So you notice that even though these were in the negative section, right, they're under the x-axis, because they have a positive slope, you end up with positive acceleration. All right. So on to the distance, which you'll see from here, is the area under, or in this case, over a speed versus time graph. We're going to have to cut everything into triangles and rectangles. So first section ends here. I have a rectangle that is 2 high and 1, 2, 3, 4, 5, 6 wide. 2 times 6 is 12. I have a triangle part that is 12 wide and 1, 2, 3 high, so half base height. 3 times 12 would be 36, and then keep only half of that, gives me 18. Well, it's not 12 wide, it's 6 wide. So what have I got here? 6 times 3 would be 18. Keep half of that is only 9. Here we go. So in this first section then, I'm covering 9 plus 12 is 21 meters. This section here, 2 wide and 1, 2, 3, 4, 5 high. 2 times 5 would give me 10 squares inside that section, so there's 10 meters traveled. Now, this section is interesting. If you recall from the multi-phase problems, there were three actually, places where you would split into a new phase. The first one was when your acceleration changed. So that's what I've done here, right? You can see each of these sections has a unique acceleration. The second one was when your object reverses direction. So that's happened right here, that this object was traveling forward still until that exact point at 9 seconds. So I'm going to split this particular section into 2. So C part 1 and C part 2. In part 1, I have a triangle that is 1, 2, 3, 4, 5 units high and 1 unit wide. So 5 times 1 would be 5. Keep half of it because it's a triangle. Gives me 2.5 meters. Now in this section, I also have a triangle that is 1, 2, 3, 4, 5 low, right? It's down 5 from the x-axis and 1 wide. So that's going to be 5 times 1 is 5, keep half of it, is 2.5, just like the other one. But I'm going to need to be able to differentiate between the distance covered going forwards and the distance covered going backwards. So the way we accomplished that before was to take any negative distances or any backup distances and make them negative. So I'm going to toss that in there. So this section here is 1, 2, 3, 4, 5 below the axis, so -5 of height, and 2 wide. So the area of that will be negative 10. The area of this one here, I have a rectangle that is negative 1 high and 2 wide. That's negative 2 meters. Here I have a triangular section that is 1, 2, 3, 4. It has a height of negative 4 and a width of 2. So base times height, 2 times negative 4 is negative 8. Keep half of it is only negative 4. So in this section, I have negative 6 meters. Last one to go. I have another final triangle that has a height of 1 and a width of 3. So base times height, 1 times 3 would be negative 3 because it's underneath. Keep half because it's a triangle, gives me negative 1.5. So that section is negative 1.5 meters. So analyzing this particular graph, up until the point where the individual came to a rest right there, they had traveled 21 plus 10 is 31, plus 2.5 is 33.5 meters forward. Then the vehicle or the object, whatever they're riding in, starts to back up, and it backs up 10, then 6, that's 16, and another 1.5 is 17.5. And if you add that all up as a total, we're going to end up with 16 meters forward of their original starting position. So wherever they started, they went forward 33.5, backed up 17.5, which net leaves them 16 meters ahead of their original starting position. So I'm going to use this idea that the distance is the area under a speed versus time graph in order to construct a distance versus time graph here from the speed versus time graph of a particular action. So this particular device seems to be starting at a speed of negative 2, and then its speed is increasing by 1 every second. So it has an acceleration of 1 meter per second. So if I were to do this by areas, so I need to start off by telling you that the initial distance is 0. So I'm going to start at this particular location. In the next second, from here to here, I have one block that's underneath and a half block that's underneath. So in that first second, because distance is the area under a speed versus time graph, this amount of area is going to come off of my initial position. So if I have gone backwards 1.5 squares, then 1 second in, I should be backwards 1.5 squares from where I started. In the next section, I have dropped another half square. Right? There's half a square colored in there, so I have to drop another half square. And if you were to check the area in that in total, you notice there's -1 here, -0.5, -0.5. That's -2 in total. And if you look, my dot is sitting right there at -2. In the next second, because I've crossed the x-axis on a speed versus time graph, the object has stopped going that way, come to a rest, and starts to go this way, starts to go forwards again. In that second, it gains an extra half unit of distance. So up an extra half. Right? Now if you were to total these, -1, -0.5, -2, plus a half would be -1.5, and that's where this dot is sitting. In the next second, I add a full meter and another half. So a full meter and another half would be here. And if you look, I have two full squares colored in under the axis and two full squares colored in above the axis. Those two things should neutralize each other so that we get back to our original position. And if you think about that, this thing was going backwards and then turned around and came back. So at some point, it's going to have to cross its original position. And our graph here just showed us that it happens at 1, 2, 3, 4 seconds into this action. In the next section, I have 1, 2.5 extra squares. So 1, 2.5 extra squares. In this section, I have 1, 2, 3.5 extra squares. So a half plus 1, 2, 3. In this section, I have 1, 2, 3, 4.5 squares. So 1, 2, 3, 4.5 squares. And perhaps you see a familiar shape showing up here. This isn't a line. This has created a parabola. So by doing the area under my speed versus time graph, I end up generating parabolic distance. Now that shouldn't surprise you because the equation that we were using quite frequently was this, where t and t squared both appear. So that's not any different than making this y equals something x plus something x squared, right? The shape would be the same. So when you do this, you can generate your parabola. Now, going the other way, if distance is the area under a speed time graph, then speed is the slope of a distance versus time graph. So because the change in this, right, dv by dt, or change in v over change in time gives us acceleration, then the change in distance over time should give us the speed. So you normally can't do the slope of a parabola. That's a thing that you don't have in your math toolbox yet. But you won't know that until calculus, and this idea is the precursor to calculus, where you're using areas under curves in order to generate a shape a dimension higher.